So in this lesson, we are going to be looking at metal extraction. So the different ways in which we can extract metals from various compounds. Now, before we move on to that, I want you to quickly just do this small exercise where you just on a piece of paper, each blue section, I want you to just write what the missing word would be. So if we just take this as 1 and this as 2, 3, 4 and 5. So I just want you to pause the video at this moment and I want you to label 1 to 5. So on your piece of paper, just put down what you think 1 would be, 2, 3, 4 and 5. Okay, so if we take the first one, this diagram is showing us the reactivity series of metals. Now, at the top of the arrow, we have most. So the most reactive metals are found at the top. So it should be most reactive. So the metals at the top of the diagram are the most reactive. Number 2, this would be the metal calcium. So you should have calcium there. So you should remember that calcium is above magnesium and below sodium. Number 3, you should have tin. So the metal is tin. Number 4, you should have gold. And number 5, you have least reactive. So the word should be least. So the most reactive at the top, the least reactive at the bottom. And for this lesson, you need to be looking at carbon and hydrogen and making note of their position in the reactivity series. Now, metals, when we talk about extracting metals from different compounds, we generally are looking at an oxidation of metals, or a metal that is combined with oxygen. Now you have here 2 images. One is of gold. So this is gold and this is sodium. Now what you will notice is that from our previous diagram, we looked at the reactivity series of metals. Now gold is valuable because it does not react with other elements. It does not form chemical compounds easily. It's unreactive in its natural state. So gold does not oxidize. So it is not found in an oxidized state. However, sodium, the metal sodium, you can see here, if you look at the diagram here, what you can see is that you've got a freshly cut layer of sodium, and you can also see on the diagram that there is a tarnished layer on its surface. So if we go here, so you can see this is the oxidation you can see has taken place here, where it's reacted with the metal and you've got sodium oxide. And you can see it is different from when it's freshly cut. So here, sodium has yet to react with oxygen, and you can see there is a difference. So oxidation occurs in metals quite frequently, and there are other chemicals that metals can bind to, but oxygen is one of the main elements that they bind to. The other one is sulfur. And for your examination, you will need to be comfortable with with the binding of oxygen and, in some cases, sulfur. Some key points down. So the first point is that metals are found in the Earth's crust. So we obtain metals from the Earth's crust. Now, previously, on the previous slide, I mentioned that they are combined with oxygen or sulfur. So I want to often metals are combined with oxygen or sulfur. We're talking about metal extraction. We generally talk about metal ores. Now, a metal ore is where there is enough of the metal in a rock that makes it worthwhile extracting. So when we're talking about a metal ore, we are saying a metal ore. So we are saying that metal ores, okay, where there is enough or significant enough, or let's say significant amount of metal. So if you're searching for copper, if you're searching for gold or silver, well, gold's not the best example because it's not found combined. But if you're searching for, let's say, copper or tin or zinc, generally it's going to be combined with other elements, other chemicals within a certain type of rock. And where there is a significant amount of metal or enough of the metal, that makes it worth extracting. Now, this worth is, I'm talking about economic worth. Now, if it's worth extracting, it's classified as the rock in which the metal is found in is classified as a metal ore. So where there is enough or significant amount of metal that makes it worth extracting from the rock. So, as I said, the first point is that metals are found in the Earth's crust. And a metal ore is where you have a significant amount or enough of the metal that you are seeking that makes extraction worthwhile, economically worthwhile from the rock. And once that is determined, it's classified as a metal ore. Now, the point of determining if it's economically worthwhile, there are 3 points to consider. One is, how easy is it to extract from the ore? So this next bullet point leads on from the last one. So I'm just going to put it in a slightly different color. So there are 3 considerations to look at before we decide if a metal ore is, if a metal is worth extracting, if it's worthwhile extracting. The first one is, how easy is it to extract? So how easy is it to extract from the ore? So how easy is it to extract the metal from the ore? Second one, how much metal the ore contains. So how much metal the ore contains. And this will be determined by the various companies that will go and survey the area, and a judgment will be made how much metal is in the bedrock, in the area, in the geographical location that they're looking at, and if it's economically viable. The third point is the changing demands for a particular metal. So the changing demands for a particular metal. Now this one, we can talk about this in various ways. If we go back, let's say 200 years, for example, lithium, it's a metal. Now, lithium 200 years ago would not be as valuable as it is now. Why? Because lithium, we use it in batteries now, and it's a high demand element because of its use in batteries and now electronic products. But 200, 300 years ago, if you were to look at the demand for this type of metal, lithium, it would not have been high. So this is an example of the changing demands for a particular metal. And as technology advances, as our understanding of certain systems advance, we may find that there are other metals also that may have a certain economical use for them or technological use for them. So this is just a quick summary of metal ores and why we extract them and how we classify metals that are chemically combined to other substances, and three considerations in determining if the metal is worth extracting. And always understand that these are economic considerations that tend to be looked at. There should be environmental conditions as well, in terms of when you start mining for certain metals, you are going to disrupt the environment and certain ecosystems. So generally, yes, companies look at economical reasons, but we also have to be careful that when we start digging for certain metals, and our extraction process as well can be energy intensive. So there is an environmental cost to mining for metals. And here we are going to look at how we can extract metal using carbon. Now, what you can see here to the side, I put the reactivity series of the metals again, and I want you to keep referring to this as I go through the theory. What you can see here is that carbon is placed in this reactivity series. You have metals above carbon and metals below carbon. Now, just as in the displacement theory of metals, a more reactive metal will displace a less reactive metal from its compound. And carbon can be seen in a similar way. So what we say is that we can use carbon to displace a metal from its oxide, from being combined with oxygen for certain metals. We can use it for zinc, iron, and tin. Okay, we can also use it for lead and copper. Silver and gold, we generally say because they are unreactive, silver, gold, and platinum, because they are so unreactive, they are found in their native states. So they are found in their pure element form in their native state. So we don't consider it here. So I would like you to put down these following statements for reduction of oxide by carbon. First point is that carbon is a non-metal. Carbon, being a non-metal, will displace a less reactive metal from their oxide. Okay, from their oxides. So carbon, a non-metal, will displace a less reactive metal from their oxides. And the metals that we have are zinc, iron, tin, lead, and copper. All right, now the next point is that you must heat the metal oxide with carbon. So the next point is that heat must be used. So you must heat the metal oxide with the carbon. All right. Next point. Carbon dioxide gas is formed. So once you heat the metal oxide with carbon, you produce carbon dioxide. Carbon dioxide gas is formed. Now, last point, leaving the element, the metal element. So you've got carbon dioxide gas being formed as a product, and also now you have the displaced element. So now we're going to look at a word equation for the reduction of a metal oxide by carbon. So the word equation that I want you to take down is carbon plus metal oxide gives metal plus carbon dioxide. Carbon dioxide is a gas, just be aware. So we have carbon plus metal oxide gives us metal plus carbon dioxide gas. Now an example of this reaction, so let's put it underneath, we'll put it in another color. So we can have an example of this reaction. We can have lead, let's do it in order. So we can have carbon plus lead oxide goes to lead plus carbon dioxide. Now, what I want you to do is give a balanced equation for this reaction with lead oxide. Now, I'm going to start you off for this equation. So you've got the standard word equation. The standard word equation is carbon plus metal oxide gives you metal plus carbon dioxide. I've given you an example of a word equation. Carbon plus lead oxide gives lead and carbon dioxide. Now, I want you to, for this equation, I'm going to start you off, and I want you to, but give the balanced symbol equation. So if I give you this formula here. So I'm telling you it's lead oxide plus carbon solid goes to lead, and here it's in a liquid state, and then we have CO2 in a gas state. Now I've given you this equation here. So lead oxide plus carbon gives us lead, which is in a liquid state, plus carbon dioxide gas. Now what I want you to do is balance this equation. So part A, I want you to balance this equation. And B, I want you to tell me why is lead in a liquid state. So just pause the video here, and on your piece of paper I want you to write the equation and balance it, and then I want you to tell me why is lead in a liquid state here. All right. Okay, so let's take a look at this. So if we had to balance this equation, what do we get? You should have got 2 here and 2 here. So this is your equation where it's balanced. Here you've got 2 lead over here. 2 lead on the left hand side, and if we take this as the right hand side, we have 2, that's balanced. 2 oxygen on the left hand side, 2 oxygen on the right hand side. We have 2 carbon on the left hand side, we have 1 carbon on the left hand side and 1 carbon on the right hand side. It was my mistake, sorry. 1 carbon on the left hand side and 1 carbon on the right hand side. So this equation is balanced now. The second part is, why is lead in a liquid state? Now, if you remember back to the points I was making about the conditions for reduction by carbon, one of them was heat, that you must heat the carbon along with the metal. So heat is required here, and because it's heat, we have made the metal in a molten state. It's in a liquid state. So because of the high heat required, the metal has melted, and that's why it is in a liquid state. Okay, so due to heat being used. Heat is one of the conditions when we reduce by carbon. The final point I want to make here is that when we remove oxygen from a compound, it is called chemical reduction. So please, can you take this down? This is an important point. The removal of oxygen from a compound is called chemical reduction. Now, the way in which we can reduce a metal oxide is via the use of hydrogen. And when we look at our reactivity series, we can see that, for example, copper is below carbon in the reactivity series, yet we've put hydrogen here. This is because sometimes it's beneficial to reduce the compound via hydrogen than carbon, because we have certain extra reactions that take place, which again make the metal that's been extracted less pure. For example, tungsten is one example. Now, before we get into that example, I want to give you the word equation for metal oxide reacted with hydrogen, when it's reacted with hydrogen. So, as we've done previously, can you put this standard word equation metal oxide, okay, plus hydrogen, and be aware, as you should be, that hydrogen is a gas, okay, gives us metal, okay, plus, and this is where it's slightly different, we get water. Specifically, we get steam. So can you just take this equation down, where metal oxide, and if the reducing agent is hydrogen, we get metal plus water, which is in the form of steam. Now, as I said, tungsten is a specific type, is a special metal that we need to, that the reducing agent here is hydrogen. Hydrogen is used instead of carbon. This is because when we react tungsten with carbon, we get tungsten carbide. Now, tungsten carbide is not a pure form of the metal that, let's say, if a company wants pure tungsten, tungsten carbide is not, it's not sufficiently pure enough. So they reduce tungsten oxide with hydrogen instead. So the word equation for the example here of tungsten, we would say, okay, let's put this in a different color. So let's say tungsten oxide, okay, plus hydrogen, goes to tungsten plus water. Again, steam. Now I keep putting steam in brackets. There's a reason for this, because there have been exam questions where you have to explain why this process is environmentally friendly. There has been a question where the question has been asked, what would the waste product of this be here? And you'd say water or steam. So just bear that in mind. There was one question I've seen where they've asked, why is this a better process? And one, you would have to, they're asking you to recall that reduction by hydrogen gives rise to water or steam, as opposed to carbon dioxide. They're just testing your knowledge on the end product. Now, the last equation, so let's do another equation where you have to balance this equation out. So let's do this one here. Now, so I'm going to give you the chemical symbol for tungsten. All right, and let's give you a hydrogen gas, and we'll say here, keep it solid, and put H2O gas. Now, I've missed out one point here on each of the three arrows. Just realized, so you should put heat. So we have heat here, heat at the top here, and heat. So all of these reactions happened under the condition of heat. We need to heat the metal oxide with hydrogen to get our metal and our steam. So what I want you to do is balance this equation that's below here. So with tungsten and hydrogen, what do we get when we reacted under the condition of heat. So just pause the video here and see if you can balance this equation. All right, okay, so you should have this 3 with the hydrogen and 3 with the water. Okay, because we have here 6 hydrogen on the left hand side, 6 hydrogen on the right hand side, and if we go to the oxygen, which becomes 3 on the right hand side, and if we look on the left hand side, the subscript is 3 here when it's combined with the tungsten. So this makes it balance. And in terms of tungsten, we have 1 on the left hand side and 1 on the right hand side. So just make sure you are practicing your balancing equations, because they do come up again in the reactivity series. I want to mention that metals higher than carbon, so aluminium, magnesium, calcium, sodium and potassium, cannot be extracted using carbon, because if you look at the chart to the right hand side, you can see that these metals are higher than carbon on the reactivity series. So what we say is that metals higher than carbon are extracted via electrolysis. Okay. Via electrolysis, where the metal is in a molten state. So the metal must be in a molten state for this type of extraction to occur. And electrolysis is a standalone topic which we will be coming on to in the next few chapters. So here you should be now familiar with the reactivity series, the position of carbon and hydrogen in the reactivity series, and its relation to the metals, to certain metals, and their extraction. In terms of what your examiner is expecting you to know, this is from your specification. So when it comes to extraction of metals, you are expected to know that unreactive metals such as gold are found in the earth as metal itself, i.e. in its pure element state, but most of the metals are found as compounds that require chemical reactions to extract the metal. So we've looked at extracting a metal via carbon and hydrogen. Metals less reactive than carbon can be extracted from their oxides via reduction with carbon, and we have gone through that one as well. And reduction involves the loss of oxygen. Okay, so just be aware of that on the word equation. The last point that was made was that the loss of oxygen is known as chemical reduction, i.e. reduction. Now, knowledge and understanding are limited to the reduction of oxides using carbon. We've looked at that. And knowledge of the details of processes used in the extraction of metals are not required. So this is important. So when we look at, there are various types of industrial processes which go into quite a bit of detail in terms of how metals are extracted. You do not need to know that. However, you must be able to interpret or evaluate specific metal extraction processes when given appropriate information. Now, how the exam questions may be structured is that you will be given a fair bit of information to actually read through, and then using your understanding of the reactivity series, the position of carbon, the position of hydrogen in the reactivity series, to answer a series of questions on that. So you need to be you need to be confident with the reactivity series, the positioning of the metals within that reactivity series, and on top of that, you need to know the position of carbon and hydrogen and why we use carbon in certain instances and why we use hydrogen in certain instances. You need to be also familiar with the products that are formed, i.e. carbon dioxide when reduction with carbon is being undertaken, and water in the form of steam when the reducing agent is hydrogen. Okay, so a quick question here. This is a past paper question. When sodium is heated in oxygen, sodium oxide is produced. Balance the equation for this reaction. Pause the video here and quickly balance this equation. It's only 1 mark. You should have you should have 4 here. Splitting the equation into the left hand side and the right hand side, quickly tally up the numbers. 4 sodium, and you have a 2 here and a 2 there. That makes 4 sodium this side on the right hand side, 2 oxygens on the left hand side, 2 oxygens on the right hand side. So this makes the equation balanced. So you should have a 4 here. Moving on to the next question. It says here, why is this an oxidation reaction? So going back to the equation, we have sodium plus oxygen gives us sodium oxide. And the question being asked here is, why is this an oxidation reaction? Why is this an oxidation reaction? So I want you to pause the video here and attempt B and C. So C says sodium oxide is added to water and shaken. Universal indicator is added. The pH of the solution is 14. What is the color of the universal indicator? So I want you to attempt quickly B and C. Each question is worth 1 mark. Your answer for part B, oxygen is added. So oxidation, oxygen is added. Very simple. Now part C, the key words here, they've given you the pH value as 14. They've told you metal plus water, so sodium oxide plus water, and it's shaken. Now, if you are struggling to understand what the theory is behind this, try and remember back to the demonstration we were looking at in terms of alkali metals, when we dropped small amounts of sodium, potassium and lithium into water. And if you remember, towards the end, I was dropping universal indicator into the solution. So the answer to this one is purple. Okay. You should have purple here. pH 14 means it's alkaline, and an alkaline solution in the presence of universal indicator at pH 14 would be purple, would be a dark purple. I want you to attempt these last 4 questions. And again, each question is worth 1 mark. Okay, now it says here, which metal is found in the earth as the metal itself? And we would say it's gold. Now you notice these are different questions from different years, so different past papers, and you can see how the questions are repeating themselves in a similar pattern. So this is why it's important that you do go over past paper questions.